So I'm just going to make Alex co-host. Okay, great. Well, welcome everybody to this week's Oxford Discrete Maths and Probability Seminar. So it's a huge pleasure to have Guillaume Chapuy speaking to us from Paris, and he's going to talk about random triangulations of surfaces, the high-genus regime.
Thank you. Can you hear me well? Yeah. So thank you very much for the invitation. I'm very honored, and you have an impressive lineup of speakers, and yeah, I'm kind of impressed. So yeah, I'm going to talk about random triangulations of surfaces, and especially at the end, I will say a word about the high-genus regime, which is kind of the pretext to talk about this, and it's based on new results with Thomas Budzinski and Baptiste Louf, who are both in France. But before talking about the high-genus regime, I will talk a little bit about random triangulations of surfaces in other regimes. And yeah, as I said, I've given a similar talk in CIRM a few months ago, which has been recorded. And so I guess if you need a recording of this talk, maybe it's as simple to go there rather than to have both videos online, but you make a decision later, apparently. So just a general introduction. So what is this about? So for decades, physicists and then mathematicians have been trying to say something interesting about random geometry, and an important motivation for this comes from quantum gravity. So as you know, in quantum mechanics, things are not deterministic. You need to integrate over the possible states of matter, for example. And if you want to do quantum gravity, you need space itself to become a variable. You need to integrate on, and not only matter. But in order to do that, at least mathematically, the least you need would be some way to integrate over possible geometries, over possible spaces. And this is something which is already kind of difficult to do. I mean, there are no good notions of random spaces a priori, and it's interesting in itself to try to understand what it can mean. And this is the motivation for doing random geometry in the context I'm talking about. So since almost 50 years in physics and more recently in math, there has been a great deal of activity in this quantum gravity, this sort of random geometry in 2 dimensions. This has become an intense field of studies. This might look ridiculous because, of course, space does not have 2 dimensions. As you know, it has at least 4 because you can see them. But still, apparently, this gives rise to very interesting physics and, of course, very interesting mathematics. So some keywords related to what I'm talking about are random maps, Brownian maps, UV gravity, imaginary geometry. I will talk only about a small portion of this. So I will talk about random maps, in particular, say, random triangulations. So here the idea will be to do random geometry by looking at a discrete random space. And this discrete random space will be made by taking at random a finite triangulation of some surface. And this will be how we do random geometry. And again, this comes from this theory of 2-dimensional quantum gravity that physicists have been considering. So it's very active. And it's very fun. One of the reasons why it's active and fun is because it's linked to many things. So it's linked somehow by definition to probability and physics, but there's a lot of connections with low-dimensional topology, in particular moduli spaces, hyperbolic geometry, and things coming from mathematical physics called topological recursion, and also to more algebraic stuff, in particular representation theory of symmetric group, algebraic combinatorics, random matrices, integrable hierarchies. So I will not talk about all this, but it's just to mention that one of the reasons why it's fun to do this sort of mathematics is because you have many ways to look at the same problem. And usually when you understand something from one point of view, you realize that you don't understand it from another. And so it's kind of a never-ending story of questions. Myself, I'm a combinatorialist. I'm a counting person. I like to count stuff. And so today, my talk will be more about like random maps. I will mostly give probabilistic statements, but in fact, counting and combinatorics will be present in everything I will say, and even more in everything I will not say. So all the proofs that I will not give, there will be a lot of counting. Okay, so let me enter more precisely my subject. So I'm going to talk about maps. More precisely, random maps. So you take an integer g, and I will consider maps of genus g. So a map of genus g is a finite graph, which is properly embedded on the oriented compact genus g surface. So for g equals 0, the surface is a sphere. For g equals 1, it's a torus. For g equals 2, it's a double torus, and so on. So this is your surface, and you have a finite graph which is drawn properly, so without crossings on it. So you can see my graph can have multiple edges. It can also have loops. And I'm considering such an object with a constraint that the embedding has polygonal faces, meaning that if you cut the surface along the edges of the graph, the pieces that remain, they are polygon. Topologically, they are disks. You cannot have a cylinder. You really need to cut all the non-contractible cycles of the surface. And you consider such an object up to homomorphism. So this is a map. So another way to think about it by construction is to imagine that you start with a finite family of polygons, for example, 1 square and 2 triangles, and you do some edge identifications. So when you do that, you glue everything. If the object that you obtain at the end is connected, you will obtain some surface. By construction, the edges of the polygon become the edges of some graph on your surface. And by construction, this is a map because the faces you started with are indeed polygons. And saying that you consider these objects up to homomorphisms is really saying that you are only considering the combinatorial type of this group. Okay, so in fact, here the only thing I'm showing you when I show you this picture is that I took some square and 2 triangles, and I performed these edge identifications. It's really a combinatorial object, even if you want to think about it as some sort of topological or geometric object as a surface. And so this is the objects I will consider in this talk. They are called combinatorial maps or maps. So people like me in combinatorics like maps because they are fun to count. There's a huge literature about counting maps. In fact, you can spend your whole life counting maps, and this is more or less what I'm doing, and a lot of other people. So there's just enumeration of maps in itself is a huge field. So just a detail, when you do counting, and then for everything I will say, I will consider rooted maps. So a map is rooted if you distinguish an edge and you orient it. This is a way to kill the symmetries. If you don't do that, maps can have automorphisms, and it's a bit less interesting. So it's convenient, and it's what people always do to deal with rooted maps instead. Okay, so these are the objects, and now I want to do random maps. So for me, random maps means this: I will take a map uniformly at random among the ones having genus G and size n. Okay, that's a random map for me, and possibly with some phase degree constraints, or some ways. But let's say some phase degree constraints for this talk. So the basic model I'm interested in is triangulations. So for triangulations, I just take 2 n triangles and I glue them in some way in order to obtain a surface of genus G. Right? There are finitely many ways to do that. I let T and G be the set of triangulations of genus G with 2 n faces. And bold T and G will be a uniformly random element in this set. And this will be my random geometry. That's the object I want to look at, and I want to say something interesting about it. At some point, I will also need this number, tau and G, which is the cardinality of this set. So the number of triangulations of genus G and size L. Okay. And at some point, I will also mention bipartite triangulation. So now what I do, I take quadrangles instead of triangles. And I color them black and white in this way in alternating colors, and I only do gluings which respect the color. And so these are called bipartite triangulations, and I let Q and G be the set of bipartite triangulations of genus G with n faces, and bold Q and G will be a random element of this set. So there is some sort of universality phenomenon which tells you that every time you have a theorem for triangulations, you expect the same theorem or a similar theorem to hold for bipartite triangulations, and conversely. But sometimes for technical reasons, it is much simpler to work with one model or the other, depending on the question you ask. And so for this talk, I've decided I will review a little bit of, I will review some results. I will always try to state the simplest and the most, like the canonical historical result, which depending on the questions is for one or the other model. But that's essentially everything is similar between them, provided you do all the math. Okay, so the question is, take this random object and what can you say about it? How does it look like? So, and I will want to do that when n goes to infinity. So I want to have this space and somehow I imagine that I'm discretizing somehow some sort of continuous space, maybe, or I don't know, to have some very fine mesh or some very large space, I don't know, but I want n to go infinity and to say something interesting. And very roughly, I can separate my questions into two kinds, so the local behavior and the global behavior. I can ask what happens around one vertex or what happens globally. And this is what I will start doing now. So is the setup more or less clear? So let me start with the local behavior in the planar case. So this is maybe one of the first results in the mathematical literature about this. So it's about the local limit in genus 0. So it's a famous result by Benjamini-Schramm. So I let n go to infinity and I take Tn0. So it's a random triangulation of the sphere, genus 0, with two n triangles. And I let n to infinity. And the result is that this converges for the local limit topology, I will say what it is, to some infinite planar graph, infinite planar triangulation called the UIPT, uniform infinite planar triangulation. So it is some random triangulation. It's infinite. It covers the full plane. It is locally finite. It's a random object, and you have convergence of your discrete objects to this infinite object when n goes to infinity. So in order to tell you, so this is convergence in distribution, but I need to tell you the underlying topology, or equivalently, I need to tell you what are the observables for this topology. What are you allowed to observe? And what you're allowed to observe are finite neighborhoods of the roots. Okay, so what you're allowed to do in this convergence is to take your favorite test map. So you take any finite map, say with M triangles and perimeter P, and you are allowed to ask about the probability that your random triangulation looks exactly like this. So you have a copy of this little triangulation around the root. Okay, and this convergence tells you that this probability for any test map that you choose converge to the same probability in this random infinite object. So this is what this local limit convergence is. And here you see, I mean, you can do it just by counting, because what is the probability that a random triangulation looks like this? Well, this is a uniform measure. So on the denominator, you put the total number of planar triangulation, which is tau n0. And here, if you remove this green piece, what you get is a triangulation of size n minus m, because you remove n minus m triangles, with a boundary of size p, which is the trace of your perimeter. Okay. And so the goal is to show that this converges to something explicit, and this is exactly what Engel and Schramm did. And the reason they could do this is because you can count. So as I said, there is a huge literature about counting maps and triangulations. And in fact, there are explicit formulas. So this goes back to Tutt. So Tutt, as you know, was a great mathematician with a lot of influence on many areas of discrete math, but in particular on enumeration, and in particular on map enumeration. He was the first to start counting maps. So you have explicit formulas essentially for all these numbers. So in fact, this is an explicit number, and you can show that it converges. And then you need to do some, you need to think, and this is what they do, to show that these numbers that appear, you can characterize them as probability to see your test map in a certain infinite random planar graphs that you can construct. And this is a UIPT, and this is what they do. So this is what I mean by controlling the local behavior, and this is a kind of an optimal result. Somehow this gives you an extremely precise description of what happens locally. It tells you anything local, anything finite that you want to fix. You know, when n goes to infinity, you can characterize the probability to see it in terms of a certain infinite random object that you have constructed. Okay, so this is kind of the best. I'm sorry, my phone is ringing. The best thing you could hope in terms of local understanding of your random geometry. Okay, so, and in fact, yeah, the same thing it will be true if you, instead of starting with genus 0, you start with genus 10 or anything fixed, you will see exactly the same. So when your map becomes very, very big, locally you don't see the fact that you have one handle or two handle or anything, and you have the same limit. So it's not written anywhere, but it's well known in the community. So I will not talk about the case of fixed genus for this local behavior. Okay, so now what about global properties? So at about the same time, there's a very important result by Chassin and Steffer, the very impressive result about the diameter. So So this is for genus 0, and then this was done for higher genus later. So if you fix your favorite genus, so now I stated for quadrangulations, but as I said, it will be the same for triangulations. If you look at the random quadrangulation of size n and genus G, and you let the size go to infinity, the diameter behaves as n to the 1/4. Okay, so this is a weird statement. So what happens is if you divide by n to the 1/4, you get a tight random variable, let's say. And the same is true. I mean, it's not only the diameter, but it's typical distances. So if you pick two vertices at random and you look at the distance, so when I say distance, I mean graph distance. Okay, so now I want to do geometry, so I need a space. So it's a discrete space. So let's say the point of my spaces are the vertices, and the distance is the distance on this underlying graph. And these distances are of order n to the 1/4. So this is something that was known in physics before, but this is really a rigorous proof of it. It's from this year 2000s. And so this is an example of global behavior, right? Because distances, of course, and the diameter in particular is something global in your object. So these are very important results, and in the next decade after this, and still now, I mean, there has been an intense activity about this, and now people can prove much stronger results, and they can show the convergence not only of finite dimensional observables like diameter or distance between finitely many points, but the convergence of the whole metric space. So it goes like this. So let's say in genus 0, so you look at your random quadrangulation of size n and genus 0. So it's a random graph, and I want to think about it as a random metric space. So you have points and you have distances between these points. So I have this metric space, and I just normalize the distance, the graph distance, but by what I should, which, as I said, is n to the 1/4. And this converges for some topology, I will say a word, to some random metric space, which is called the Brownian map. So it's a very deep result, very difficult result by Le Gall and Miamont a decade ago. And the same is true in any genus. So if you fix your favorite genus and you do the same business, you have convergence toward a certain random metric space, which is called the Brownian map or Brownian surface of genus G. And this is a very recent result by Bettinelli and Miamont. So one way to think about it, so this is an example for genus 2. If you take a very large quadrangulation of genus 2, I don't know, maybe 100,000 vertices, of course, it's huge. So if you look at it from far away, so you renormalize it by what you should, so n to the 1/4, so that the picture fits your slide. And you see something like this. What is this? This is, if you want, a realization of a certain continuous random metric space. Of course, you just have an approximation of it here. But underlying it, there is some continuous random metric space, which is called the genus G Brownian surface, here genus 2 Brownian surface. It's a random object. It's very wide. It's kind of two surfaces. What Brownian motion is two curves, if you want. It's some sort of canonical random surface of the given genus. So this is what this genus G Brownian map is. So, I mean, more formally, I mean, here you have a topology here, which is the Gromov Hausdorff distance. It's a distance that enables you to compare two metric spaces. So if I give you two metric spaces, you can try to put them one next to the other in the best possible way, which preserves distances, which is isometric, and which makes a small Hausdorff distance between them. And the smallest Hausdorff distance that you can realize is the Gromov Hausdorff distance. So it's a way to compare two abstract metric spaces together. And in this sense, you have this convergence. But you can just think about it as this picture, which I think gives you an idea of what happens. So these are very deep results. And now there is an intense activity in probability theory. I mean, people are trying to understand what these objects are, what are their fine properties. But interestingly, this also comes from counting. So the reason why this was possible in the first place, and then why this was possible later, is because they are very, very powerful combinatorial tools. And in fact, it's not only counting, but it's bijective counting. And now I will show you something kind of independent. I will just give you I mean, it's not independent, but you can look at it independently. It's the Corey-Vauclair-Schaeffer-Marcus bijection. Sometimes people call it the Schaeffer bijection. So it's something that exists in this counting literature I come from. It's a combinatorial construction that I will describe now. it has taken decades to invent it. At the beginning, the goal was not to do probability theory. It was just because some weird people wanted to have a better understanding of some explicit formulas. Okay. So it goes like this. So you start with a bipartite triangulation with n faces, and for some reason, so let's say there's a root somewhere, but I will not talk about the root. But there is a pointed vertex somewhere. Okay, so this one in red. And now I will do some construction. So I do the following. So first, I label the vertices of my graph with a distance to the pointed vertex. Okay, so the pointed vertex has label 0, its neighbors have label 1, neighbors of the neighbors have label 2, and so on. Okay. And now, I make the following observation. If I go around the face of my map, so it's a quadrangle because I started with a quadrugulation. And if I is the smallest label in my face, I claim that the other labels are either I plus 1, I plus 1, or I plus 1, I plus 2, I plus 1. Why is this true? Well, by the triangle inequalities, the distance can vary by at most 1 along an edge. And because my map is bipartite, it cannot vary by 0, because otherwise I would create an odd cycle by looking at the two corresponding geodesics. So distances vary by at most 1, and then there are only these two by exactly 1 along each edge, and so there are only these two possibilities. There are two types of faces in such an object. Yeah, so don't look at the right. For example, for now the right is it's just the same as the left. Yeah. Anyway, and now you do this. So these are called the Schaeffer rules, and it's something that you cannot invent unless you are Gilles Schaeffer. In faces of the first type, you had a blue edge like this, and in faces of the second type, you had the blue edge like this. And you do this in all the faces of your map. Okay, so let me do it. So you do this, and you get some blue graph. Okay, which avoids the pointed vertex by construction, and now you have this blue graph, and here now come a number of magical facts. So the first magical fact is that this blue graph, in fact, it is a map with one face on your surface. Meaning, if you just look at the blue graph and you cut the edges of the blue graph on your surface, what remains is one single polygon. Okay, so it's what we call a one-face map. This is non-trivial, but it is a property of this construction. So this blue graph, it's a one-face map with n edges, and by construction, if you remember the labels are one Lipschitz among this blue graph, right? Because the variation along the blue edge is either 0 or 1. Okay, so you get a blue graph equipped with a one Lipschitz integer labeling of the vertices, and the craziness of the Schaeffer bijection is that this is a bijection. It's the same to start with a bipartite triangulation of given size, or just a single polygon gluing equipped with a one Lipschitz labeling of the vertices. That's it. Okay. Well, I mean, so there are some details. You need some routing convention. You need to consider the labels of two global translations, otherwise you have infinitely many objects on the right. But if you do that, this is a bijection. Okay, so why is it interesting? So you see, so for example, let's think about the torus. In genus 1, the one-face map of the torus, so if you, a single polygon gluing on the torus is always like this. So it's formed by a kernel. So in fact, in genus 1, you have only two possible kernels. Maybe you have this graph or you have this graph. And then along the branches of your kernels, you substitute trees. And this is always the case for any genus. You have finitely many kernels. And then you substitute the edges by branches of trees. So these one-face maps, they have a very, very simple structures compared to general quadrangulations or general maps. And now, I mean, very roughly, I mean, these branches that you substitute, they will be themselves large random trees. And as you know, a random tree will typically have diameter square root n. And now, of course, you don't have only the tree, you also have this one Lipschitz labeling that plays a role. But this one Lipschitz labeling, if you take it at random, along the branches of each tree part, it will behave as a random walk somehow. And the increment of a random walk along a branch of length square root n will be square root of square root n. So the typical order of this label will be n to the 1/4. And this is exactly how you prove this Chassin-Schaeffer result about the typical distances in the map. Okay, because these labels, they are the distances in your original map. This is how you started the construction. And this bijection and then many other generalizations for triangulations, for all sorts of maps with some constraints, they are the starting point for all these diameter estimates and also for all these Gromov Hausdorff limits. Okay? So these fancy results by Le Gall and other people with these very subtle continuous metric spaces, at the beginning, they relied on these weird constructions made by weird combinatorics that just wanted to have fun inventing little rules. Okay? So that's something important to remember. This form. Okay, so in fact, in the first place, I mean, so the reason why these constructions were designed was for counting. So people wanted to, so there are some counting results, which usually are not obtained by combinatorial techniques at the beginning. They are obtained by algebraic means or maybe by some complicated generating functions calculations. And then when you see them, you want to understand them. So the result, the counting result, which is at the basis of this story, is a very important result from the 90s by Bender and Canfield. So no, this is about counting. There is no random object anymore. But so the result tells you that if you fix G and you want to know the number of maps of size n, say quadrangulations, for triangulations, you would have a variant of this. It behaves as follows when n goes to infinity. So you have something like 12 to the n, which is related to the entropy of these three branches that you have to add. And then you have a polynomial correction, which is 5 half G minus 1, which is universal. It will be the same for triangulations, quadrangulation, or whatever. And then you have some numbers TG in front of it, which are complicated by a very complicated recursion on the topology. And the previous bijection explains this very well, because somehow for any fixed genus, you say, okay, I need to put a certain number of branches of trees together, but trees you can count, you know how many branches you have to glue together. You also have constraints, because when you do a gluing, you have some constraints on the labels you have to glue. But all the end, you do some sort of smart calculation, and you find these exponents. And so in the end, this kind of picture, I mean, and this Schaeffer bijection was designed in particular in high-genus to get an understanding of this Bender and Canfield formula. By the way, for people interested in mathematical physics, this paper by Bender and Canfield is really the prehistorical example of the Hénin-Orentin topological recursion, which is some fancy business in enumerative geometry right now. And this is kind of a very basic ancestor of it. This is really a very important paper for many different areas of mathematics. Okay, so this, from the viewpoint of combinatorialists, from my viewpoint, this is something we understand. But then there is something we don't understand at all. These numbers TG that appear here, in fact, they are also very simple. At least there is a very simple procedure to compute them. So these numbers TG that tell you which is a constant in front of the enumeration of maps of genus G. There is a simple quadratic recurrence to compute them. Essentially, TG plus 1 is either something times TG or a quadratic convolution. I mean, it's not for TG, but for this rescaled version where you have a gamma function. And so this is hard to attribute. This is related to the integrable structure of generating functions of maps to matrix integrals. But let's say that it has become well understood, at least since 20 years. And so this is really very combinatorially happening. This suggests that you have some surface of genus G is always obtained by either gluing two smaller surfaces in an additive way on the genus, or by taking something with one genus less and doing some construction. And this is a combinatorial mystery. Okay. So for people who know about random matrices, this is essentially what is called the double scaling limit in random matrix theory. It comes from if you reinterpret random matrices as a function of maps, and if you perform what people call the double scaling limit, you have at some point you have a Parevet-1 equation which turns into this recurrence. But combinatorially, it's a mystery, and for people like me, I mean, this is the main, the main new question, even if this is proved, and there is no doubt about the fact that this is proved, but is to find a combinatorial interpretation of this, and we cannot do it. But still, as I said, this map enumeration is a source of new and weird questions. So let me just state a conjecture, which I like, and Christina also likes. Conjecture I made a long time ago, much before this date. Because for some years I tried to prove it, but failed. So take a Brownian surface of genus G, or if you prefer, fix G and take a very, very, very large random map of genus G, quadrangulation, for example, and uniformly at random. And then you pick 2 points on it, uniformly at random, P1 and P2. And now you do the Voronoi tessellation. So you separate your object into 2 pieces. You put on one side all the points which are closer to P1 than P2, and on the other one, all the points which are closer to P2 than P1. And you call xg, the fraction of points in the first set. It's a random number between 0 and 1. And the conjecture is that this number is uniform. It's a random variable, and it's a uniform of the order. And well, this is open. I mean, it's been proved only in genus 0 by a physicist, Emmanuel Guiter. Well, there's an analog statement for k points where the similar, the simplest analog of this holds. I mean, it's conjectured to hold. And in fact, the second moment of it, so the fact that the second moment is the one of a uniform, which I think is 1/6, is essentially bijectively equivalent to that. So I'm able to produce some sort of combinatorial construction that explains this formula, but at some point, I'm stuck with Voronoi diagrams with marked points and so on, and I need to know that this is true in order to confirm. But in the end, this motivates a more general conjecture that tells us that, I mean, so far, all the big random geometry people, Le Gall and these people, they have no idea why this should be true. Right? So there is some interplay between random geometry and counting that each of them reveals things about the other and asks new questions. And so there are many things that we don't understand, even for fixed genus maps. So essentially, we understand fixed genus maps, but how do they vary when the genus moves is a question that is not so well understood. Okay, so that's what I wanted to say about this fixed genus map. So I told you the local behavior. You can look at finite neighborhoods of the root, and you have this convergence to this kind of infinite planar graphs, UIPT and so on. And globally, you have convergence to these random surfaces after normalization by n to the 1/4. And then you can try saying stuff about these random surfaces. And in both cases, this is very much related to the fact that you can count either like numerically or, I mean, with formulas or bijectively. Okay. So now I would like to do something else. I would like to do maps where the genus is not fixed. Okay, so what can I do? It's not fixed, or at least it grows with n. So the first thing I can try to do is the completely unfixed genus case. So I can just let n go to infinity and do not impose any constraint on the genus. But I mean, this is very, very different. So you take 2n triangles if you want to do a coordination, and you just take any edge identification. So now all the groupings are essentially independent. You don't have any global constraints, except that maybe you want a connected object. So if you know what this is, I mean, this is much closer to what people call the configuration model in random graph theory, right? You have like cubic vertices and you link them together. So it's interesting. You can say many things. In some sense, it's much easier. I mean, the basic questions are much easier because you don't have this topological constraint. So you can say, of course, you can still study it, but then you will be able to say much stronger things. So the genus will tend to be almost maximal. You will have an object with very, very few vertices. The vertices will tend to be very, very glued to each other. The genus will be almost maximal. So it will be like n/2 minus little o of n, I think something logarithmic. So you can say many strong things by various methods, and there has been a revival of interest by Curien and co-authors about this recently. But let's say that for me, this is a very different business because somehow you lose this constraint of topology, so you lose the whole flavor of all these things we are doing. So what I will do instead is to try to have n and g, I mean g be fixed, I mean g be controlled, be imposed, but go to infinity with n. So I will try to have a map where both the genus and both the size and the topology go to infinity at the same time. And this is what I will call the high-genus regime. And for some reason, which will be maybe at least I will be a motivation in 1 minute. What I want to do is to take g proportional to n. So we want to take g over n to go to some constant theta, which will be positive, but less than the maximal value, because the maximal value will be essentially the same as the unfixed genus case. So I want it to be restricted in an open interval between 0 and 1/2. And this is what I call the high-genus regime. If I do a small calculation, so if I have, so if I do a triangulation with two end faces, the number of edges is 3n because it's a triangulation by double counting. And by Euler's formula, number of vertices is n plus 2 minus 2g. So you see that the average degree, which is twice the number of edges divided by vertices, is something like 6/1 minus 2 theta plus little o of 1. And so if theta is positive, this is strictly larger than 6. Okay. So if theta was equal to 0, or if g was a little of n, this would go to 6 as in the planar case, or fits in this case. But if theta is strictly larger than 0 and strictly smaller than a half, then this is some number which is strictly larger than 6. And so somehow this tells us that we expect something different. We should see this in the limit. In fact, we expect something of, in some sense, of hyperbolic nature. You have some sort of curvature. Around the vertex, you don't have average degree 6, and as in a plane triangulation, you have something, you have more degree, you have more vertex degree locally. So this is some sort of curvature effect, if you want, or whatever this means at this stage. And so this is one of the motivations for studying this regime. You expect really something that is intrinsically different, something in the end. So this is, I'm just rewriting the same thing here. So I fix theta, so less than half, and I consider maps whose genus Gn is like theta times n. And so it's fun. This model is fun because it's difficult. Right? So we do not have independence as in the configuration model. We really want to control the genus in the end, so we cannot just throw edge identifications at random. We have a complicated global constraint. And also we cannot count. So there is nothing in the combinatorial literature that tells you what is the number of triangulation of genus theta times n when n goes to infinity. There is no such things. And of course, these bijections that I showed you, they still work, but some of the reason why these bijections are useful is that because you reduce your objects to a finite number of kernels for a given genus. But here, the number of kernels grow with the genus because the genus grows, and so you don't know what to do with it. So these bijections, I mean, at least maybe they are helpful, but it's not clear at all. So this is why, I mean, so technically speaking, it's fun because you cannot do it, and then there is a kind of a reward that you expect is that you expect to discover some new behavior related to this hyperbolicity that I was talking about. So in fact, there is one model. So we started, I mean, people started to think about this maybe a little bit more than a decade ago. And there was one thing we could do, which was this one face case. So it's a toy model. So you just look at a random map with one face. So you take a one single polygon with two end sides, and you do some gluing in such a way that you have something of genus G in the end, and that's your model. So it's not a triangulation at all, or a convolvulation. It's just a map with one face. It's a toy model of random geometry, but this high-genus regime is so hard that the toy model is already interesting somehow. And 10 years ago, we were able to do both the local and global limits. So with co-authors, we did the local limit, which turns out for this toy model to be some sort of infinite random tree, which is super critical. So with balls that go exponentially, so really you see the hyperbolic nature already in the toy model. And Gura Brai in his PhD thesis showed that the diameter indeed is logarithmic as well. Yeah, so I have not said it, but the fact that the diameter is logarithmic is one of the things that you would expect if the model has this kind of hyperbolic flavor. In particular, if balls grow exponentially, you expect that after logarithmically many steps, you absorb the whole space. Okay, so this we were able to show, I mean, to obtain hyperbolic behavior both locally and globally 10 years ago. And the reason is that for this toy model, the combinatorial tools are very powerful. So you have counting results that go back to Lehman and Walsh in the 70s. And you have also very powerful bijections that go back to, say, my PhD thesis. And as before, I mean, you use these ones for the local behavior and these ones for the global behavior. But since then, I mean, it was an open problem to do anything about the general case. So, in fact, even this toy model has been revived recently. There is work by Baptiste and Dante Janssen. Because even in this toy model, you can study some sort of statistics, like the length of the shortest non-contractible cycle or things like this. And you discover strong analogies with the results that have been obtained by Mirzakhani about random Weil-Peterson surfaces, which a priori are something completely different. And so people are getting excited about this, trying to find more such analogies and try to explain these analogies. But going back to the main question, so of course we tried in 2012 and later to study the general case. So for example, triangulations, not the toy model, in the high-genus results. And until recently, this was really I wrote science fiction because there was no hope of doing it. We had no tools, and it was just it looked really impossible. There were conjectures, in particular conjecture of Benjamini and Curien, telling you what the answer should be, but it was just too hard. So of course, since I'm talking about it, something happened, and indeed something happened. So in 2019, there was a breakthrough. So an inventionist paper by two PhD students, Thomas Budzinski and Baptiste Louf, who now have jobs in France. They proved the so-called Benjamini-Curien conjecture, which tells you what is the local limit in this high-genus region. So it goes like this. So you take, you let n go to infinity and g go into infinity as theta times n, where theta is between 0 and 1/2, as I was saying. And you look at T and G, so a uniformly random triangulation of size n and genus G. Well, for this local limit topology, it converges to a certain object called the sheet of parameter lambda. So it looks like this. So it's again an infinite triangulation of the plane, except now maybe it makes more sense to draw it as a triangulation of the hyperbolic plane, hence this picture. So it is for the same topology as before. You look at observables which are neighborhoods of balls and probability to see a given neighborhood, neighborhood of the root. So you look at the probability to see the given neighborhood of the root. And so you have this convergence. So what is this sheet? It is some hyperbolic analog of the UIPT in which balls grow exponentially fast and they are parameterized by an extra real parameter lambda. So this was something introduced by Curien. So I did not tell you what this uniform infinite planar triangulation is. It is some sort of infinite planar graph. So in fact, you have an algorithm to construct it. So essentially, you grow a triangulation of the plane. You start by putting one triangle, and then you add triangles to the boundary one at a time and bring it in some way. So sometimes you just glue it to the boundary. Sometimes you glue it to another piece of the boundary that you have already done. And you have rules, and you have a certain algorithmic probabilistic way to do this. And in the end, you construct an infinite triangulation of the whole plane. And in this sheet, you reproduce essentially this algorithm, but you have an extra real parameter that biases a little bit the process and somehow makes your ball go a little bit too fast. And so you obtain an object which is very similar in its construction to the UIPT, but which goes a bit crazy and somehow explodes exponentially. And this is what the sheet is. And this is why you have one real parameter to parameterize it, because you have the freedom of this parameter to tell you how much the process has become wide. And here also I have one parameter lambda, and there is an explicit function lambda of theta that Budzinski and Louf give you to tell you how they are related. So this theta will control in the end somehow the exponential growth of the final object that you obtain with this parameter lambda. So this was really a very impressive result, and it's also an impressive paper. So they do not go, as I was saying, in the planar case. So it's not that you can count the numerator and you can count the denominator and then you divide and you have some convergence. Because as I said, it's still an open problem to count these things. So they have something much smarter. They have some sort of surgery argument that show that certain observables are bounded, and from this they use some compactness argument, so saying that somehow the limit is, the process is tight in some sense, and then they have a more probabilistic argument to study the space of possible limits. In the end, they get to the sheet. So it's very fine in both combinatorial and probabilistic arguments. So this is really a conceptual breakthrough, and we get this very strong result. Yeah, and so it requires very little combinatorial input. What I mean by this is that they don't start with the counting. In fact, there is some input. I will say a word about this, which is this Goulden-Jackson equation obtained from the KP hierarchy. I may say a word about it later. But so remarkably is that not only do they start from the counting, but in fact, they obtain the counting in return. So a corollary of their result is this. So it's an estimate for the number of triangulations of size n and genus G when G is theta times n. And I tell you, it goes like this. So it's n to the 2g. So n to the 2g is huge, right? Because g is linear in n. So this is more than exponential. And then you have an exponential part, exponential of some function of theta times n plus little o of n. And this function of theta is something that you can plot, something completely explicit. So you see, I mean, this is far from a true equivalent, right? Because it's an estimate up to exponential little o of n. So exponential little o of n can be extremely big. Okay, so in particular, you cannot take ratios of two such things and conclude that it will converge to anything. But this is the best we can do. Right? This is like really the state of the art from a very impressive paper. This sort of counting estimates. Okay, and it comes as a byproduct of the whole machinery that they developed. Okay, so now what is the next step? And this is what I'm talking about. And these are in fact the new results in this talk. So here I tell you about the local behavior in high-genus. So the next thing to look at is the global behavior in high-genus. Okay, so as I said, you expect things to be logarithmic because if balls grow exponentially, then objects should have logarithmic diameter. And this is exactly what we prove. So with these two smart young people, so we get global properties in high-genus. So in the same setup, so you have G proportional to n, G proportional to n. So G is theta times n with theta strictly between 0 and half. Then the diameter is logarithmic. So with high probability, meaning with probability going to 1 when n goes to infinity, the diameter will be bounded between two deterministic constants times log n. So this is something, as I said, we've been trying to do for a decade. And but of course, this builds on the previous breakthrough. So in fact, we had the first proof that was using these bijections, and then a lot of complicated stuff. But at some point, we realized that the bijections are not really necessary, so we removed them from the picture. And in fact, the proof essentially boils down to an isoperimetric estimate, which in some sense could be also seen as the main result. I mean, as the diameter. So let me state it. I will read it and then I will try to explain what it means. So in this setup, so G is theta times n. So you have constants K and delta, which depend on theta. Such that if you take any K1 and K2 that sum to 2n, which is your total number of faces, such that K1 and K2 are not too small. So the smallest of the two, K1, should be at least K times log n. Then there is no multi-curve of total length delta times K1, the smallest of the two, which separates your triangulation into two components of sizes K1 and K2. Okay, so let me do it again. So what's a multi-curve? It's a collection of cycles that can touch but do not cross, and that cut your surface into two pieces. So you want to find such a multi-curve and end up with two pieces of size K1 and K2. You want to be able to do that, okay? And so what I'm telling you, so let's say that K1 is the smallest of the two. If K1 is too small, so if it's less than K theta times log n, I cannot tell you anything. Yeah. But if both numbers are large enough, so if K1 is at least K theta times log n, then what I tell you that the number of edges that you need to cut has to be comparable to K1. You need to cut at least the constant times K1 edges. Okay. This is some sort of this is why we call it isoperimetric. Like it tells you if you want to cut a piece, well, the boundary of this piece, I relate the size of the size of the boundary you need to cut in order to cut a piece of a certain size. It has to be proportional, except for very small pieces. Okay. So if you know about the Chigger constant, this is very much related to the Chigger constant, right? So if you have a graph, so maybe here this will be the Chigger constant of the dual graph, but it also works for the primal. So the Chigger constant, what you want to do, you want to take, say, a subset of faces, and you want to compare the size of the boundary with the size of the set itself. Okay. So of course, if you take the whole space, this will be 0. So you don't want to take the whole space. You want to take something which is at most half the total size. I have two n faces, so I take at most n faces. And I want to compare the size of the boundary with the number of faces that I've taken, and the smallest such ratios that I can make, I call this a Chigger constant. Okay. And well, this sort of isoperimetric inequality gives you one direction, right? Because somehow if you cut something which is big enough, you will always get a constant here. And so only things of size log n will be able to contribute, and they will never do better than 1 over log n. So this will give you one direction for the Chilier constant, and for the other direction, in fact, we can prove relatively easily that logarithmic tentacles exist. So in some locally, you have pieces in your graph. You just have a very small cycle of length, I don't know, 2 or 3, and from it you have something of logarithmic size which is angry. This gives you the other direction. So this is this is kind of meaningful geometric information about your surface. So these are our two main results. There were no proofs so far in my talk, and there will be no proof at all. But I can give you an idea of what happens. Maybe some idea of things that happen. So for isoperimetry, we do something very conceptually very simple. We just do the obvious thing, which is kind of first moment method. So you just, if you have a picture like this, you cut your triangulation into 2 pieces. So you start with something quoted by tau ng, triangulations of size n and genus g, and you obtain 2 pieces which has size n1, g1, and size n1 genus g1 and size n2 genus g2. And one will be essentially k1 plus something proportional to the length, because you need to retriangulate your boundary. Okay. And you want to say, you want to compare this ratio, essentially this divided by this. And you see in the Budzinski Louf estimate, something that helps you is you have something like n to the 2g. So since g is linear in n to the 2g is really something that goes very, very, very fast. And so this ratio, n to the 2g divided by something where we have essentially cut things into 2 pieces, will tend to be very, very large, exponentially large, unless one of the 2 pieces is very small. And then, but then, this is not enough. You want something which is very fine at all scales, because you want to control everything up to logarithmic scale. And so you need essentially to have refinement of these estimates. And this is what we have. So we have refinement of this estimate essentially that enables us to take ratios of things and not only estimate one given number, but ratios of such numbers. And just want to mention one thing, that this function f is explicit in the work of Budzinski and Louf, but in fact it's a terrible technical challenge to prove that it is concave. And it's crucial in our proof. And in fact, we thank Andrew L.V. Price, who actually proved for us that this thing is concave. It's like a 2-page proof with calculations, but in fact, we couldn't do it without him. Anyway, so this is a sort of argument, but so it relies strongly on the Budzinski proof estimates, or more precisely on their proof that we are able to refine. Then 2 words about the diameter. So to lower bounding, the diameter is also something very, something very easy, because this is also, again, first moment. You take 2 random points, x and y, and you want to count the number of paths of length L between them. And then what you can do, you can cut your surface open along this path and retriangulate the inside. And if you do that, you obtain a triangulation. You start with a triangulation of size n and genus g, and you obtain something of size n plus L and genus g. But the Budzinski Louf estimates tell you that these ratios, tau n minus 1 divided by tau n, they are bounded by a constant. They converge to this constant lambda. So when you do this sort of ratio, tau n plus L divided by tau n, you get something to the L. And in return, because here you have taken 2 points at random, and here only 1, you have an n minus 1. So it's very easy to see that if L is not logarithmic, this will go to 0, and by first moment, there will be no such path. Did I say it wrong? Maybe I said it wrong, but it is a simple first moment calculation based again on this bounded ratio lemma by Budzinski. So last thing I want to say is, why is isoperimetry related to distances? So this is something I think kind of classical for people used to expansions of graphs and this sort of things. So it gets a little bit technical in our case, but basically the basic observation is this. So you take your favorite vertex and you grow balls. So say you look at the ball of radius r. So this blue thing here, where r says already something logarithmic. And then you look at the pieces which are separated by the boundary of the ball. So you have pieces here in green which are separated by small boundary components. But by isoperimetry, you know that small boundary components, they can only separate small things. So this will be something you can control, thanks to the isoperimetry. And on the other hand, you have places where the boundary of the ball is very large, say comparable to the size of the ball itself. But if this is the case, I mean, in a triangulation, if the boundary of your ball has size L, this means that you have L new triangles that are growing on it. And maybe some of these triangles are the same because you have edge identifications. But one triangle can appear at most 3 times. So you have something that tells you that, I mean, at least locally around such a component, the number of new things that you get at radius r plus 1 is at least what you have at radius r plus 1/3 of the size of the boundary. So if the boundary is comparable to the size of the ball itself, it means that you're in a place where you're growing exponentially. And if you grow exponentially, you're happy because you cannot grow exponentially for more than logarithmic many times, right? And so essentially, by isoperimetry on the one hand, and this kind of, I mean, isoperimetry tells you that either you're in control or you're growing exponentially, and from these two things, you get logarithmic diameter. And so this is what we do. And I think, I mean, as I said, there are analogs. There are also logarithmic bounds for diameter of random Weil-Petersson surfaces, and I think the proof in Mirza-Kani's papers are also using this sort of expansion arguments. This is something classical. Okay, so I'm done. This is my last slide. So this is a very biased introduction to random maps. I just want to mention that all introductions to random maps are, and my only hope is that I was biased differently compared to other speakers who sometimes do not know that they are biased. So counting results play an important role in all the proofs that I didn't give, so including bijections, the topological recursion, and also something I only mentioned by name, which are these integrable hierarchies like KP and Tutodas, which are related to a much more algebraic side of the story, the fermionic Fock space, random matrices, and representation theory of the symmetric group. This is the completely different connection in the world of map enumeration to algebra. But it has some important consequences. So let me mention one now, which is related to the things we cannot do. So there are things we cannot do, and the most basic one, it may be very difficult. I mean, we have tried for many years. The most basic question is this, and if we could answer this question, this would trivialize all the, I mean, many results in this one. In particular, the Budzinski Louf paper in invention will become trivial if we could do this. Can you give an asymptotic equivalent of 2ng, a true equivalent, not up to exponential little of n, but a true equivalent when n and g both go to infinity? The answer is no. I mean, we cannot do that. And this is extremely frustrating because, in fact, you have an explicit formula to compute these numbers. So you have this tau and g. I mean, let's say you rename them f and g after some scaling. These f and g, they are computable by an explicit quadratic recurrence, which is due to Goulden and Jackson, and which is a consequence of this algebraic combinatoric stuff. So when you see such an equation, you would believe that with a little bit of math education, you are able to obtain an estimate for these numbers. And maybe you are, but so far we aren't. Okay. And and this is very much related to all the business I talked about before. And another thing that we cannot do, I mentioned it already, but I like this question so much that I will mention it again. It's about this Voronoi tessellation. So I repeat the conjecture: take a random map of genus G and take k points. No, I do it for k points. You take k points uniformly at random on it, and you look at the Voronoi tessellation, and you look at the proportion of points in every cell. The conjecture is that this is a uniform random variable on the simplex. And we have no idea why this would be true, except from the fact that I did this conjecture many years ago and that we can prove some very special cases. And with Christina, some years ago, we proved that, in fact, the same thing is true for random trees. And but we have no idea why, in fact. Why would a random space have uniform Voronoi tessellation? This is a question that has nothing to do with maps in itself, but I keep asking to people, hoping that someday someone will have an idea. And I'm done. Thank you.
Thank you, Guillaume, for a really beautiful talk. I enjoyed that enormously. Does anybody have any questions? I know that Alex does, so I'm going to let him unmute and ask his, and other people can think of theirs.
Yeah, Guillaume, thanks for a lovely talk. I think logarithmic tentacles is my new favorite phrase. So I actually wanted to ask about, so in this very high genus regime, how much do you feel that locally? So kind of how, as you, I mean, you've got logarithmic diameter, but as you kind of grow balls, how much do you feel the genus?
So this is what Budzinski and Louf are telling us here. So locally,
I guess I don't know what the limit object looks like. So
yeah, so the limit object is it is some sort of random triangulation of the plane that you can construct inductively. So you start by a triangle and you glue some new triangles every time. But when you glue new triangles, you essentially have you have two ways of doing it. Either you glue a single triangle, or you take one piece of the boundaries that you have already seen and you glue it back to the rest of the boundary. And so you have a certain parameter. You have a real parameter that tells you which probability you do one or the other. And so if you bias, if this parameter is critical, you will get exactly the UIPT. And if it is slightly supercritical, you will get something where the balls grow exponentially. And this is this parameter that governs the limiting object. And this parameter is related to the genus. So this theta times n. You have a certain function lambda of theta, which I think is injective. So I mean, it's like a strictly monotone. And so you really, I mean, you feel the growth of balls. The exponential growth of balls is really related to this parameter theta here. I mean, in the way I just said, hoping that I was clear. Is that clear?
So I guess what I'm not quite clear about is, does the lack of planarity appear locally, or is it just in the limit objects you get many accumulation points as you grow?
So the lack of, no. So locally you don't see the lack of planarity. So the limiting object is planar. Mm-hmm. The limiting object is planar. This is what they prove. In fact, this is the starting point of their proof. They managed to prove this, and then from there they use some compactness arguments. It is planar, but there is still a trace of this parameter theta in the fact that in this planar object, the balls grow exponentially, and the constant behind the exponential is related to theta.
Okay, thank you.
I think Oliver has a question. Oliver, go ahead.
Yes. So, I mean, you've got these kind of tentacles and things where locally strange things happen. So do you get sort of stronger bounds on the typical distance between vertices, where you kind of assume that your local configuration is normal, is typical? Because I guess that would, that your restriction in the isoperimetric thing that it only works above log m, you kind of might be able to get round that for typical points somehow.
Yeah, I will say something. So in fact, so we prove something a little bit. So we prove something else, which is that essentially almost every pair of points is at the same distance of the other. So it's like if you take 2 points and you look at the, I mean, if you take 4 points, the distance between 1 and 3 and the distance between 1 and 2 and between 3 and 4 it differs only by a constant. So like all the distances are kind of the same in this object, and for almost all points. And so I'm not sure this answers the question, but this is one thing we can say. So in fact, we have conjectures for this. So we have a conjecture which may be provable about the length of the longest tentacle. So the longest tentacle will be something like a constant times log n with a deterministic constant. And in fact, we believe that if you take 2 points at random, the distance between them is also a constant times log n. And I think the constant is even the same. And so in the end, the diameter will be 3 times this constant times log n, because you will take the 2 longest tentacles and plus the attachment points, which essentially behave at random points. So these are the sort of things that we can guess.
Like in the Hansen result for random graphs, there's a 1, 2, and 3 times log m. Forgotten exactly what the.
Yeah, exactly. So there is some analogy with random graphs. And the question is, what can we prove? So far, I mean, in the paper, we don't do anything like this. So it does not prove, it does not completely unfeasible, but there are definitely some technical issues in getting these sort of results.
But it sounds like you have a strong result for typical distances, or maybe not absolute bounds, but that they're all very close to each other.
Yeah, this we can prove.
Okay, that's very nice.
It's also a consequence of the isoperimetric.
Mm-hmm.
Okay, great. I think that's a sensible place to stop. So I'm going to stop the recording, and I'm going to suggest that people unmute themselves and give Guillaume a big round of applause.